All right, so we're going to pick up where we left off last time, talking about these electrophilic aromatic substitution reactions. We're going to start linking them together, doing multi-step reactions here. But first things first, let's just practice reviewing two of these reactions that we learned how to do. I want everybody to take a second and try to draw me my product. And I want you to try to do it without looking back in your notes, all right? A big problem that I see students when they're studying with organic chemistry is they're always studying with their notes open. That's a great way to signal to your brain that you don't have to remember that information because you know where to look, right? Unfortunately, our brains are lazy, and it doesn't bother committing stuff to memory unless we force it to. A great example is back when I was a kid, you memorized everybody's phone number because that's all you had, right? Now, I couldn't even tell you what my mom's phone number is because it's just so easily accessible in my phone, right? Because I know where that information is and I can easily find it, my brain doesn't hold on to it, okay? So again, always a good idea. Once you have to practice with your notes open a little bit, but you need to get to the point where you're studying without your notes open. You're doing these problems without your notes open because that's, of course, going to simulate your testing environment. All right, so in all of these reactions, we're substituting this hydrogen for a different group. What are we going to put on in the case of this set of reagents here? What's our product? We actually know the name of our product here. Bromobenzene. Right? We have a bromine now in place of that hydrogen on our ring. And what about in our next example? Nitrobenzene, putting that nitro group, that NO2 group on there. Cool. All right, so this is just practicing two of those reactions, but again, our punchline for today is going to be talking about multi-step EAS reactions. So what happens if I did this bromination reaction first, and then I did my nitration reaction second? All right, or we're going to swap the order here. What if I did my nitration reaction first and my bromination reaction second? Okay? It turns out that you will get a different product depending on which reaction you perform first. Okay? So this first reaction, I put that bromine on my ring. My next reaction, I'm going to put a nitro group on my ring, just like we'd expect. But the question is, where does it go? All right? Is it going to go in one of these positions right next to that bromine? We call those what positions? No, right next door. We got those ortho, meta, para designations, right? So right next door is ortho. Do I put it in the ortho position? Do I put it in the meta position? Or do I put it on the opposite side of the ring in the para position, right? That would give me a different molecule depending on which position I add that nitro group to. So it turns out if we do the bromination reaction first and then our nitration reaction, we'll get a mixture of two products, the ortho product and the para product. But if I take these same two reactions and all I do is I switch the order in which those reactions take place, now all of a sudden I only get one product. I get my meta product. All right, so same two reactions. In both cases, I've added a bromine and a nitro group to the ring. but the order in which I perform these reactions is going to dictate what my product is. Again, in the first example, we had our ortho and our para product. In the second example, the same two reactions, just in reverse order, gave me our meta product. All right, so the bottom line is, for these multi-step electrophilic aromatic substitution reactions, the order of those EAS reactions will dictate what your product is. Okay? So you're just trusting me here on these products. We haven't gotten to why this is yet, being able to predict this ourselves. But this is my point I'm trying to make here. We're going to be doing these multi-step electrophilic aromatic substitution reactions where we take those 6 reactions that we learned and we start mixing and matching them. All right? And what we're going to find is the order in which we do these reactions is going to dictate what our product is. All right? So why is that? Why did I get these 2 different products? So we're going to take all those groups that could be on our benzene ring, and we're going to throw them into one of 2 buckets. All right? They're either going to be electron donating groups, or electron withdrawing groups. And we're going to talk about the donators first. All right, so an example of an electron donating group would be a hydroxyl group, adding an OH to our ring. We have a special name for this molecule here. What's this molecule's special name? Phenol. All right. And what we're going to see is this pair of electrons here, this lone pair, can be donated to that benzene ring. Okay? We're going to illustrate this electron donating business by drawing all the possible resonance structures of phenol. All right, so here's my phenol. Oops. And what we're going to see is it can donate a pair of electrons to that ring. Boom. All right, now, I can't stop there with my resonance structures because I'll have broken my octet rule. This carbon would now have 5 bonds. So at the same time, what has to happen is this pair of electrons jumps up onto that carbon. All right, I want everybody to take a second and follow these electron pushing arrows. Draw my product, my other resonance contributor that I would get here. All right, and you want to think about those 3 possible categories. Are you looking at a bond breaking, bond formation, or both arrow? This first arrow here would be which one? Bond breaking, bond formation, or both? This is a bond formation. Starting at that lone pair is always a bond formation arrow. So now I have a carbon-oxygen double bond, which means what do I need to add to my oxygen? Formal charge, yep, that positive formal charge. And then this one down here is a what? Breaking, formation, or both? So this is a breaking. And oftentimes when we start at a pi bond, we do see that both pattern. But this particular one, it isn't reaching out and grabbing another atom. It's just jumping up to that carbon. So this would be a breaking arrow, meaning that pi bond is going to become a lone pair on my carbon. So this is one of our resonance contributors of phenol here. And we can keep going. That pair of electrons we're going to see gets passed around this entire ring. All right, so now my lone pair has moved. And I've reformed one of those pi bonds. All right, and there's actually one more that we can draw. So everybody's going to take a second, put in our last electron pushing arrows on this structure and draw me my last resonance contributor, continuing this pattern here. Alright, so my last one, again, that pair of electrons comes to form that pi bond, and that jumps up onto that carbon. Alright, so to be clear here, we drew these resonance structures of phenol. Why did we draw these resonance structures of phenol? Because we were going to illustrate that electron donating of that group. All right, so convince yourselves that what you're looking at when you're looking at these resonance structures is this pair of electrons got donated to that ring, and now we have this negative charge that's being passed around, stabilized by that ring. Okay? First of all, so remember with resonance structures, if we're being really good, and we're not, we're so lazy all the time, and we just draw this as our molecule of phenol. But if we're being really good, then we draw all of our resonance contributors, and we remember that our real molecule is a hybrid of all of these together. All right? When you draw those multiple resonance structures, your true molecule is the hybrid of all those resonance structures, all smashed together. They're kind of all true at once. Now, although they're all true at once, they're not all equally stable. If we want to just take these two examples here, our regular old phenol versus this first resonance structure that we drew, which one do we think is the more stable resonance contributor? The one on the left or the one on the right? The one on the left is going to be more stable, right? This one has a bunch of formal charge. So our true molecule of phenol looks more like this most stable resonance contributor. But again, all of these resonance structures are true at once. And what you're going to find is these less stable resonance contributors are often very key for the chemistry of that molecule, right? So just because they're unstable doesn't mean that they don't matter. Good advice for life too, okay? So these unstable ones here are how we're going to understand the chemistry of this molecule. Importantly, our electron donating groups are what we call ortho para directors. okay? Meaning that they direct incoming groups to the ortho or para position, ortho and para position. I lied, we're going to say or. You don't get both at the same time. All right, so to be clear, in our first two examples that we looked at here, bromine would be considered an ortho-para director, because when we added bromine to the ring, the next substituent that we added was directed to the ortho and the para position. Okay, so these electron donating groups, they're ortho-para directors. And now we're going to look carefully at these resonance structures, and we're going to try to figure out why. Right? Why would electron donating lead to these ortho and para products? All right, well first, to explain why, we're going to remember that benzene plays the role of what in these EAS reactions? Nucleophiles or electrophiles? Nucleophile. So benzene plays the role of a nucleophile in an EAS reaction. And nucleophiles are what? The thing that's electron rich or electron poor? They love that positively charged nucleus because they themselves are electron rich. Yep, so yes, our nucleophiles are electron rich. All right, these electron donating groups they change the nucleophilicity of that benzene ring. All right, let's look here. Do we think that this is going to make, this electron donating group is going to make benzene a better or a worse nucleophile? Does it make it more or less electron rich? Looking carefully at our resonance structures here, did we make that benzene ring more or less electron rich? More. We're adding electrons. We're donating electrons to that benzene ring, right? So electron donating groups, they make benzene an even better nucleophile. Right? I've added electron density to that benzene ring from my electron donating groups. But let's look real carefully here. Which positions got that extra electron density? We have electron density, extra electron density here, here, and here. So relative to that OH groups, what positions are these? The ortho and the para position. So why are these electron donating groups ortho-para directors? Because they make benzene a better nucleophile, specifically at the ortho and para position. Okay, so some of our groups on our benzene ring are going to be electron donating groups, and those are ortho-para directors because they make those ortho and para positions even better nucleophiles, adding electron density. All right, so they're going to direct an incoming substituent specifically to that position in an EAS reaction. All right, our other bucket are not electron donating, but rather electron withdrawing groups. All right, so an example of an electron withdrawing group is benzaldehyde. Got that carbonyl group right next to the ring. All right, and what we're going to see is that carbonyl group is going to, instead of add, it's going to withdraw or pull electron density from that ring. All right, again, we're going to use our resonance structures. And we're going to use that to illustrate that electron withdrawing. All right, so for this one, for the sake of practicing our electron pushing arrows, what I'm going to do is I'm going to give you the other resonance contributor, and you're going to draw in the electron pushing arrows that we need in order to get there. So I'm going to need a bond breaking arrow to turn that pi bond into a lone pair on my oxygen. And then I'm going to need one of those breaking and formation arrows to move that double bond over. All right, leaving me with a negative charge on my oxygen and a carbocation. All right, so again, just to kind of be good here, this was a bond breaking arrow. And this one was a both, breaking and formation. Right, and kind of how you want to think about these breaking and formation arrows here. We have this pi bond, it's going to swing over to form this new bond over here. All right, and just like before, I can keep on going. I can bounce this positive charge around my ring by drawing more resonance contributors here. All right, and I'm missing one more. Y'all are going to fill in for me here. Take a second to complete this series. right, so these are all of our resonance contributors of benzaldehyde. We can see that electron withdrawing group has pulled electron density from the ring. So now I have positive charge that I'm bouncing around that ring, right? This electron density has been removed from the ring. All right, it turns out that these electron withdrawing groups, these are what we call metadirectors. All right. So again, let's look carefully at our resonance structures and try to answer why these things are metadirectors. Okay, well again, we're going to remind ourselves what role benzene's playing in this reaction. Again, benzene plays the role of that electron-rich nucleophile. These electron withdrawing groups they're going to make benzene, what do we think, a better or a worse nucleophile? A worse nucleophile, because now they're taking electron density out of that ring, all right? So these electron withdrawing groups, they actually react slower than benzene does. They take electron density away from the ring, making benzene a worse nucleophile. But again, it turns out that not all of these positions are equally as bad. Specifically, where have we removed electron density from? Which positions? The ortho and para positions, right? So the reason why this is a metadirector is because I've made these ortho and para positions absolute crap nucleophiles by taking the electron density away from those ortho para positions specifically, right? So our electron withdrawing groups make benzene a worse nucleophile specifically at the ortho and para positions. All right, leaving only the meta positions able to be nucleophiles. All right, so what we did was we took our example, our benzaldehyde, and we drew all these resonance structures to illustrate this electron withdrawing effect. And what we saw is we're pulling electron density. Now we have this positive charge that is being bounced around this ring, and that positive charge is specifically bouncing to the ortho and para positions, which is why our incoming substituent is going to be added only to those meta positions. All right, so again, our groups that we add to our benzene ring, we throw into these two buckets: electron donating groups, which are ortho-para directors, and electron withdrawing groups, which are meta-directors. So let's take all that and see if we can't do one of these multi-step reactions that we were talking about. All right, we'll try to practice a few more of those reactions that we talked about. Let's do first a Friedel-Crafts acylation reaction. Let's do one fluorocarbon. And then we're going to do a chlorination reaction. All right, so everybody take a second. Following these two steps here, draw me my product of our multi-step electrophilic aromatic substitution reaction. so I'm going to break it up into these two reactions so you can kind of see a little easier exactly what's going on. Okay. This first reaction, I'm going to put this, what we call an acyl group, on that ring. I'm attaching this molecule here, but specifically at which carbon? What's going to be the one bonded to our benzene ring here? I'll call them carbons 1, 2, and 3. What do we guess? It's going to be carbon 3 here. Our carbonyl carbon is what gets bonded to our ring. Remember, we got that acylium ion intermediate with that positive charge on that carbonyl carbon. So this is what I would get after that Friedel-Crafts reaction. All right. My chlorine and aluminum chloride is going to add what to the ring? What do these reagents do? They're going to add a chlorine. Okay, great. So the question is, which position do I add the chlorine to? So I got to look at what's already on the ring here and figure out whether this is an orthopara or a meta-director. And this, with its carbonyl group bonded to the ring, is which one? Meta. This is a meta-director. So I'm going to be adding a chlorine, or rather substituting out a hydrogen for a chlorine, but specifically in that meta position. You could have picked either of these two meta positions. Either would work, right? But you're going to add a chlorine to the meta position, not to the ortho or para positions. And I just want to point out, it was what was already on the ring that dictated where that incoming group went, right? It wasn't the chlorine that gets to decide where to go. It's what's already on the ring that's going to direct that incoming substituent to a specific position. What's that?
Is it safe to assume that when we see a carbonyl, we're going to go to meta-directing?
Yeah, so we'll like this fell into a very specific example that we've already seen. We're going to look at our big broad categories here in a second, right? So now how do I classify any of these functional groups that I could look at? Okay, for that I've got this big ugly cheat sheet here, and you can find this slide posted on Canvas under our introduction page. You don't have to worry about like frantically copying this down. All right, but what we're going to note here, and we're going to pick apart certain features, is we have either orthopara or meta-directing groups. All right, and we've thrown them into these categories based on being either strong, moderate, or weak. Okay, we have our electron donating groups. These are classified as activators, meaning they react faster than benzene. Our electron withdrawing groups, which make that benzene ring an even crappier nucleophile, these are deactivators. All right? Well, let's just go category by category here and point out important structural features. So our strong orthopara directors. A good example here would be that phenol, that one that we saw before. But if we look at all of these strong orthopara directors, we'll see that they share that common feature that phenol had of having that lone pair directly next to the ring. Okay, so our strong activators, our strong electron donating groups, these all have those lone pairs next to our benzene ring. Our moderate orthopara directors. At first glance, they have also those lone pairs directly next to the ring, but what else do they all share in common? That carbonyl group on the other side. And what do we know about carbonyl groups? Are they electron donating or electron withdrawing? Withdrawing. So these do have a lone pair that they can donate to that ring. but they also have this carbonyl group pulling that lone pair away as well, right? So even though they can donate that lone pair, they can't do it quite as well because of that carbonyl group. All right, so these also have that lone pair next to the ring, but with a carbonyl on the other side. Okay. Our next category are these weak orthoparadirectors. And what do these weak orthoparadirectors all have in common? What are we looking at here? What atoms are in all of these groups here? Hydrogens and carbons, right? These are just these alkyl groups. Carbons and hydrogens, all single bonds. All right, so these weak activators are alkyl groups. All right, they have no electrons to donate, but they still make benzene a better nucleophile through what's called hyperconjugation. Which we're just going to leave at some magical force that is making these benzene rings better nucleophiles. All right, our next category are also weak orthoparadirectors. And what do these all have in common? Chlorine, bromine, iodine, what family they belong to? Halogens, all right? So these are all our halogens. And halogens are kind of in a weird category because they do have pairs of electrons that they can donate through that ring, but they're also very electronegative, and they withdraw through what's called induction. So they've kind of got this push-pull where they both donate and withdraw from the ring at the same time. All right? So halogens, they can donate their lone pairs, but they also withdraw through induction. All right, our next category, now we're into our meta-directing groups. So we have these moderate meta-directors here. All right, and what structural feature do these moderate meta-directors all have in common? That carbonyl group, right? That carbonyl carbon bonded to that benzene ring. All right, there are two oddballs on the end here, okay? Our sulfonic acid group, and this is a really important one to commit to memory because we know how to add that sulfonic acid group to a ring using that fuming sulfuric acid, all right? So this one here is also a moderate as well as a nitrile group. We'll talk a little bit more about these carbon-nitrogen triple bonds, but they tend to behave a lot like carbonyl groups because you have this high-order pi bond to a more electronegative element, all right? So these are all our moderate meta-directors. All right, we have carbonyls. We're going to note those two special ones, our sulfonic acid group and that nitrile group. All right, and then our last category are strong meta-directors. Unfortunately, these don't really have any structural common feature. Luckily, there's only 3 of them, so they're not that hard to remember, okay? We have our nitro group is a strong electron withdrawing group. We illustrated this when we first introduced this nitro functional group, okay? Importantly, also one to note, because we know how to make it using nitric acid and sulfuric acid, we can make a nitrobenzene. This aminium ion here is also a strong electron withdrawing group. And lastly, if we have a carbon that's fully substituted with halogens, that is another strong electron withdrawing group, another strong metadirector. All right. We want to note this one as well, because this is another one that we know how to make. So let's remind ourselves. We talked about these reactions at the benzylic position. So if I take toluene, for example, what happens when I react this molecule with NBS? What did that one do? Does anybody remember? Somebody said bromine. Yeah, so we had two reactions at this benzylic position. One was an oxidation reaction. One was a bromination reaction. NBS here will brominate, put a bromine on that benzylic position. And if instead I just dump in a crap ton of NBS, a large excess, it will fully brominate that carbon. Bless you. All right, so this would be one of our strong metadirectors. Cool. So again, this is under the introduction page of our chapter 16 module on Canvas, this little cheat sheet here. But yes, we got the world broken down into ortho, para, or metadirectors, and then we further broken them down into these categories of strong, moderate, and weak. All right, so what's the strong, moderate, weak business doing for us? Let's take one last specific example here. Okay. All right, I want to take this benzene derivative here, and I want to do a Friedel-Crafts alkylation reaction. I want to stick a methyl group on this ring. All right, so we got to look at what's already on the ring to figure out which position that methyl group is going to go. All right, so what I want to do is I want to look, and a nitro group belongs to which one of our categories here? So this one, a metadirecting group, and in fact a strong metadirector. So that means that that nitro group wants to direct that incoming substituent to these positions that are meta to that nitro group. All right, what about our sulfonic acid group here? Going back to our cheat sheet. Our sulfonic acid group is also a metadirector, but it's a moderate metadirector. So it wants to direct that methyl group, that incoming substituent, to those positions that are meta to it, to that sulfonic acid group. And we see there's a conflict here, right? Nitro wants to direct to the purple carbons. Our sulfonic acid group wants to direct to the orange carbons. So which one do we think is going to win? The strong one, right? So that's what those strong, moderate, weak categories are for, is if we have a conflict, and we won't always have a conflict. Sometimes they'll point to the same place. But if we do have a conflict, the strong one will win, all right? So when we draw our product here, we're going to draw our methyl group in that meta position. All right, this is meta to the nitro because the strong wins. All right, so we got one more category of reactions of these benzene derivatives to learn, but then we're just going to kind of rinse and reuse over and over again. We're going to spend a lot of time next week practicing these reactions. All right, so before you come in next week, you're going to have completed your first electrophilic aromatic substitution reaction, basically just making sure that you've practiced all of those reactions that we discussed so that you know what does what, right? So that when we start mixing and matching them, we know what we're talking about here. So get that initial practice down, and then we'll start making things more complicated, chaining them together, all that jazz.